with my PhD students Tong Yuan Li on incorporating local climate zone into community land surface model. So I would like to start with this slide. In recent decades, China has experienced a very rapid urbanization process with both increase in urban population and also expansion of cities. And in some projects, it says we will have maybe nearly 1 billion urban population in 2025. And to me, I think maybe we have been there. So okay, now in nowadays, urban heartland may be observed in nearly almost every city in China, and both in service urban heartland and also candidate urban heartland defined by the near surface air temperature. And before we talk, when we talk this with some local government or some vendors, they usually ask two questions. So, what's the reason cause urban heartland, and what we can do for the mitigation? So, thanks to a lot of previous studies, especially Dr. Li Zhao and Dr. Stanley that is here in this room. Now we have a very useful tools for urban heartland attribution based on land surface model. Basically, this method expands the surface area balance equation using first order Taylor expansion, and then we can get the contribution factor to urban heartland be split physically. And here I just show example the IBM method developed by Dr. Zhao, and we can see the urban heartland contribution can be divided into net radiation and aerodynamic resistance and the change on power ratio and so on. And this method is what we used in this study. And but in current published studies, the mostly the urban area are taken as a whole. So the urban inner heterogeneity is not well considered, mostly due to the limits of the land surface model, because community land surface model is now widely used in such studies. And in current release CLM5, only 4 suburban types are considered, basically only on building density, and there are tall building districts, high, middle, and low density urban area. But this was really in the heterogeneity in cities. Just to show some example in Sydney or in Shanghai. And the local command zone has been proved be a very useful method to represent the urban inner heterogeneity, especially a lot of studies have been carried out in such as urban thermal condition analysis. And what we have done is we replace the urban description in CLM with local climate zone by modifiers called to handle more urban subtypes, including from local climate zone 1 to 10, and create new land use dataset based on a very high resolution LCD map, and create a parameter table for each local climate zone, and create initial condition input for different local climate zone. And after such a modification for CRM, we do the evaluation with our observations in Nanjing city with both flux observation. We have eddy correlates flux observation carried there from 2010 to 2014. Unfortunately, we lost the tower now. And also, another data set that we use to do the evaluation is weather station observation from Nanjing city. And 3 cases are designed with different forcing data and different land use input for the urban description. And the first one is forced by the tower observation and use the default urban description in CLM. And we only three urban classes are considered because in this area we don't have tall building. And the simulation domain is about 1 kilometer by 1 kilometer is about the 90% footprint of our flat tower observation. And also, the third one, we changed the forcing data from a regional forcing database developed by Tsinghua University. It's called Chinese Methodological Forcing Data. It's widely used for the land surface, offline land surface model running in China. And the data resolution is 0.1 degree. And also, first, we take a look at the flat observations. And after we consider local climate zone scans in our simulation, we have increments mostly on sensible heat flags and heat storage simulations. As shown, the blue line is a new model simulation, and the orange line is observation. And also, for the regional simulation, the third case just covers the whole Nanjing district area, and we used 36 weather stations, and we classified them into different local climate zone types based on their location and the surrounding area, and we compared the simulated canopy air temperature and the relative humidity with the observations, and the results show they agree with us relatively well. And furthermore, we carried out a long-term simulation covering whole eastern China, including most urbanized area in China. And the simulation period is 20 years, and the first data is CLM5 as mentioned before. And in this talk, we only focus on the results of 2030, because in this year, a very nearly 1 month heat wave occurred in eastern China and covered mostly all the eastern China. And also, we divide our simulation domain into different subclimate zones from north to south. We have south subtropical and middle and non-subtropical, and then warm temperature and temperate and middle temperate. Then as previous talking this session, we can see we can calculate urban heatland use both surface temperature and near surface air temperature, and also we can use the maximum value and the minimum value, and we can output a lot of urban heatland intensity based on our simulation. And in this slide, I just show the sensible urban heat island and canopy urban heat island based on the maximum and the minimum calculate. And we can find the surface urban heat island are always much higher than the canopy urban heat island, and also the varies depending on the in different climate zone, and usually peaks in the middle subtropical area. And also, if we take a deeper look into different local climate zones, we also can see the difference. For example, usually at nighttime, local climate zone 1, the compact high rise, usually have a higher urban heatland both in surface and in the canopy. And in the daytime, it goes quite different. Usually, the canopy urban heatland appears in some kind of LCD4. It means open high rise. And then at time, and for the surface urban heatland, it usually goes to LCD8 is something like the light low rise. And also the urban heatland over different local climate zone varies varies in different subclimate zones. Also, based on Dan and Lee's work, we also can circulate the contribution factor of surface urban dataland, and we also can see the spatial variation over our simulation domain, and also we can see in different local climate zone and in different suburban background climate background, the computing factors maybe do different uh, behaviors different. And for example, for the this is the aerodynamic resistance. Usually contributes more in the middle subtropical area and very less in the warmer temperature. And usually the contribution of isopropylic heat flux will decrease with the uh, local climate zone change from compact high rise to specific. Also, we can separate our simulation results from heat wave events and no heat wave days based on 83.3 percentile based on Bose results. And this is a relatively low threshold because we just want to get enough sample for each wave. So and the difference between the heat wave and non-heat wave days can be taken as how the heat wave will enhance urban data. And also we can find that the most enhancement occurs in non-subtropic area and in for the daytime and for canopy urban data, it usually occurs over local climate zone 7, but at night it occurs over all local climate zone, local climate zone 1. And also we can change our percentile to define the heat wave date, and we can gain such a protocol like this. The number from 1 to 10 indicates the different local climate zone, and the number from 85 to 99 indicate the percentile we defined heat wave and non-heat waves. And we also can see the contribution factors of to the surface urban data line varies in different ways. For example, the heat storage maybe to a negative contribution in a very strong heat wave emissions and in local climate zone, but the contribution will become weaker with the change on local climate zone and boost the intensity of heat wave events. And for example, the contribution of naturalization maybe doing little contribution at night and even in daytime, we only have a smaller variation in these plots. Okay. Also, with this with our simulation, we can give a detailed spatial and temporal distribution of the thermal comfort index, which have been employed in CLM model. And quick summary: we just coupled local climate zone schemes into CLM5, and we do benefit from this because we can get detailed urban heat island distribution and thermal comfort. And also the next plan is we need more data for the evaluation and more input parameter data. Especially, I believe Dr. Zhang's team is working on a global continuous high resolution data set. And before I end this talk, I would like to appreciate Dr. Yongwei Wang's team for the 120-meter resolution LCD data in China, and please read our paper. And we also share our codes in this paper, and so you can do your own simulation if you want. Okay, thank you.
Do we have a question? Time for one.
Thank you for that presentation. So I have two quick questions. First, maybe I missed that. Where did you get your kind of key parameters corresponding to the implemented LCD?
Okay, so currently we just use the table from Oak's book, Urban Climate Zone. So they just for each local climate zone, they have a range for each
Yeah.
parameter, and we just take the median value.
Okay.
Okay.
The second question is that it seems like in your case, the UHI is much larger by using the Tmax than Tmean, which is a conflict with the previous speaker.
Oh I think okay. I think usually if we take a look at the surface urban line, it's usually we have a much higher max urban line intensity because we think for the surface urban line usually dominated by the net radiation and the surface energy balance directly. So we have a strong radiation income. So we got strong urban heat island. But for the canopy, it's not the truth. I say it's quite similar to the previous talk in this session. Yeah.
Rob,
Can I just
really quick.
Yes, very impressive. I'm a little bit surprised that the nighttime contribution is not mostly from the heat storage, but from the bone ratio. Why? In the attribution part, did that surprise you?
But I need to. We're still looking on this because it's only 1 year, and it's 30 year is a long month heat wave, and we just compare the specific 1 year to our last 20 years simulation. And maybe we can talk about this later.
Thanks, Ning. Thanks again. So next up, we have Ling Zhang presenting.